Okay, so this topic ties together everything that we've done so far in this chapter. So what we're going to be doing are going to be calculating equilibrium concentrations from an equilibrium constant, and we're going to do this by writing an equilibrium expression, and then building our reaction, our ICE table, and then solving for X so that we can find what the equilibrium concentrations are. So our first step, before we can do anything, we need to make sure that we have the reaction equation and that it's balanced. Fortunately, here in this question, they give us all the information we need. Here's the reaction equation. They balance it for us, and they tell us the number of moles of each substance and the volume of the flask. Now, this looks just like the previous topic. This should be easy because from this information, we can find the initial concentrations and begin to fill in our ICE table. Okay, so let's find the initial concentration for each of the substances. For H2, for I2, and HI. So I'm going to put a little not symbol there to indicate initial. So initial bracket concentration for each of the three substances. So the initial concentration of I2 is going to be the number of moles of I2 divided by the volume in liters that it's occupying. The initial concentration for HI would be the number of moles of HI divided by its volume in liters. And initial concentration of H2, well, it's saying that at the beginning of the reaction, we don't even have H2 to start with, so it is 0 molar. We don't have any at all. All we have is this, and the reaction will proceed. So let's get our concentrations here. We have 0.1 divided by 0.5. That is 0.2 molar. We have 1.6 divided by 0.5. That's 3.2 molar. Okay? We have our beginning concentrations. Here they are, our initial concentrations. Let's plug these into the ICE table. Okay? So 0 moles H2, initial concentration is 0. Here's the reaction. So this is for H2, this is for our second reactant, and here's our product. 0.2 molar for I2, and for HI, 3.2. So we have quite a large high concentration of HI to begin with. Okay, so the flask is filled with this and this. We don't have any of this. You may wonder, oh, how do we get this? Well, this reaction is reversible. Not only does this and this come together to form hydrogen iodide, but hydrogen iodide also decomposes into these two substances. So spontaneously, hydrogen iodide will decompose into this, adding more, but also into this. And then the hydrogen and iodide also can react together to go back the other way. So this reaction goes in both directions. Okay, so our next step. Let's determine what the change in concentration is going to be. Well, in order to determine what the change in concentration is going to be, I need to be able to predict which way this reaction is going to go. Well, obviously, the reaction is going to move more in this direction because we don't even have any hydrogen gas to start with. So this is going to be plus X. The change in concentration from the initial, which is 0, is going to be some positive value. It may not be a lot, but it's going to be some positive value. Okay? So because this is a reactant, iodine is also a reactant, the change in concentration is also going to be plus X. What's the change in concentration going to be for hydrogen iodide? Well, for every 1 mole of this that's made, 2 moles of this is consumed. This is a product, so while the reactants is plus X, the products will be minus 2X. We just pull down the stoichiometric coefficient here. Okay? So our equilibrium concentration, I just add straight down. 0 plus x is x. 0.2 plus 2x is 0.2 plus x is 0.2 plus x. And 3.2 plus minus 2x is 3.2 minus 2x. Okay? So now we have used algebra to determine how we can calculate the equilibrium concentrations by letting x represent the change in concentration. All right, so what's the next step? Well, we begin by finding our initial concentrations. We took those initial concentrations, plugged them into the next step, which was the ice, our reaction table, plugged them in here. We determined what the change in concentration was going to be, and then we use algebra to create this expression telling us what the equilibrium concentration is. Okay? So what do we do next? Well, next, this is what we do. We look at the problem, and we see that they give us K for this reaction. Ask yourselves, how do we find K again? You remember, K, and since we have concentrations, I'll use Kc. Kc is equal to the products raised to their stoichiometric coefficients over reactants raised to their stoichiometric coefficients. Well, they give us K. Say it's 3.06. So if I know K, I can work backwards to find the equilibrium concentration. So let's write this equation out. Kc is equal to, what is our product? Hi squared over H2 times I2. And that came from the balance equation here. Okay. Now, if you remember, this is the equilibrium constant, and we find K, the equilibrium constant, by knowing the equilibrium concentrations of all of the substances. So this is the concentration of Hi at equilibrium, H2 at equilibrium, I2 at equilibrium. Okay? Well, we don't know these equilibrium concentrations, but we know that what they are equal to. The equilibrium concentration of H2 is equal to x. The equilibrium concentration of I2 is equal to 0.2 plus 2x, and the equilibrium concentration of Hi is equal to 3.2 minus 2x. What if I took these and substituted them here and took what we know K to be, 3.06, and substituted that here? Then we can work backwards and solve for x, and then just plug x in here and have our answer. So let's do that. K is 3.06. What is Hi equal to? 3.2 minus 2x. So 3.2 minus 2x squared divided by H2 is equal to x. So x times I2, which is 0.2 plus x. 0.2 plus x. So at this point, we have our equilibrium constant expression. We've made substitutions. We plugged in K, and we plugged in the expressions that we found using algebra to represent the equilibrium concentrations of each of the substances. So our last step here is to solve for x. So what we need to do is simplify this. Okay. So this is the hard part. Some of you all may find a lot of different apps to help you to do this. I encourage you to do the math, okay, to do the math yourself. But there is one app that I found that's pretty cool. I wish we had these apps when I was in school. Photomath. I had no idea that it existed, and came across it, and it makes this really easy. You could take a picture of this, and it will give you an answer, or will help you to solve these long, drawn-out processes. So I'm ashamed that I showed you guys this shortcut, but when I plugged it into my Photomath, it took me straight to the final answer. Now, you still have to know how to interpret that answer, but it's useful to know that you can always check yourself. And I would definitely use it to check my work, but I encourage you guys to do it the long way. Work it out by hand so that you can figure out what you're doing yourself, okay? So let's proceed forward. So we have this from our equilibrium constant expression that we substituted all these values for. Now let's simplify it. Let's work this out, okay? So what's our first step? Well, the first thing I want to do is take this from the bottom. Let's distribute it out. So I'm just going to work through it one step at a time in my own way. There are many different ways to approach this. So 3.06 is equal to, let me write this out. And then we can distribute it over 0.2x plus x squared. Next thing I'm going to do is bring this up and over. 3.06 times 0.2x plus x squared is equal to, that's 3.2 times 3.2 is 10.24 minus 3.2 times 2 minus 6.4x minus 6.4x, and then negative 2 times negative 2 is going to be 4, so plus 4x squared. Let's combine what we can here. I get 10.24 negative 6.4 plus another negative 6.4 is negative 12.8x plus 4x squared. And over here, 3.06 times 0.2 is 0.612x plus 3.06x squared. Okay. The next thing, let's bring everything over to one side. And I think the easiest way to do that would be to bring everything over to the right, since most of what I have is over here. So let's subtract 3.06x squared from both sides, and I get, so if I subtract 3.06 from both sides, I get 10.24. It cancels out over here, minus 12.8x plus, so 4 minus 3.06, 0.94x squared. And let's subtract 0.612x from both sides. And so I get 0, there's nothing over here now, is equal to 10.24. I have negative 12.8 minus 0.612x. I get 13.412x plus 0.94x squared. Okay? And the last thing I want to do is I'm going to rearrange this, and I'm going to rearrange it to make it represent a quadratic expression. So the quadratic expression is ax squared plus bx plus c is equal to 0. Okay? Or 0 is equal to ax squared plus bx plus c. So let's rearrange this. And what I want to do is I want to put this in front. Okay? Don't necessarily have to, but I'm just doing it for myself. So I'm going to put 0.94x squared. What's bx? This is bx, and it's minus, so I got to keep the sign. Minus 13.412x, and then what's c? This is c, and it's positive, so I keep the sign. plus 10.24 equals 0. Okay? I didn't move anything to any other side. I just shuffled them around so that they represent this. All right, so here we have our quadratic expression. Okay? Because we have this quadratic expression, well, it still hasn't given us x, but there's a very, very useful thing that we can use to solve for x if we have a quadratic expression. That is the quadratic formula. So let's move forward. What is the quadratic formula? Well, the quadratic formula is x is equal to negative b plus or minus the square root of b squared minus 4 times a times c, and all of this is over 2a. Now we have plus or minus, so we actually can get two values for x. So we'll see how to determine which value for x is the correct one. So over here, let's do the plus. X is equal to negative b plus the square root of b squared minus 4ac all over 2a. And over here, let's do x is equal to negative b minus the square root of b squared minus 4ac all over 2a. Okay, let's go back and let's figure out what a, b, and c are. This is a, this is b, this is c. Pay close attention to the sign in front of each value: positive, negative, positive. Okay, so we're going to plug it in. X is equal to negative b. B is negative 13.412. So this will be positive 13.412 plus b squared. So negative 0.412 squared is 179.88 minus 4 times a, 0.94, times c, 10.24. And this is all over 2 times a, which is 0.94. Okay, so x is equal to, let's solve this first and then we'll plug it in. So 4 times 0.94 times 10.24, that's 38.502. So 179.88 minus that is 13.412 plus the square root of 141.3776 all over 0.94 times 2, 1.88. Simplify it some more. 13.412 plus the square root of 141.3776 and then we're going to divide by 1.88. And in my calculator, I get x is equal to 13.4586. Okay, that's one possibility. So let's do the other side and figure out what the other possibility for x is. We've already done this and this, so I'm just going to copy it over here. The only thing different is that this is minus and this is plus. Okay, so these values should still be the same until we get to the very end. Okay, and we change that plus to a minus. So doing the same work, I should get 13.412 minus the square root of 141.3776, and this is x is equal to all over 1.88. So x is equal to So let's see what 13.412 minus the square root of 141.3776 is, and divide that by 1.88. And I get x is equal to 0.80945. Okay? Now these are concentrations. How do I know? Equilibrium concentration, change. X represents that change in concentration. Okay? So if these are initial concentrations, what's the change in concentration? So that's what we found here. So how do I figure out which one is right and which one is wrong? Well, here's the key. One answer is impossible. And it's always going to be that. One of your values for X is going to be physically impossible for this reaction. The question is, which one? Well, which one of those is going to be impossible? It looks to me that the clear answer is this value for X. Because look at how large it is, 13.45. I don't even have that much here. So if my initial concentration was 3.2 molar and it changed by 2 times X, 2 times 13 is 26, I don't even have that much of a concentration to start with. I can't have a negative concentration, right? Can't go below 0 for a concentration. It's either there or it's not. Whereas here, this is so small, 2 times 0.8 is about 1.6. That will still leave me with some. If I start with a concentration 3.2 molar, and if it's decreased by 1.6 molar, I still have some left. So that makes more sense, okay? So in this case, my impossible answer is this one. And I'm going to go with this for X. So let's take this value for X, 0.80945. Notice I didn't round too early on any of my values. The more you round, the more precision you take away from your answer. So try not to round these too much. 0.80945. Okay, we're going to plug it in here. We found that X is equal to 0.80945 molar. Okay, so let's take X and plug it into our expressions for the equilibrium concentration and get those answers. So what is the equilibrium concentration of H2? What is the equilibrium concentration of I2? What is the equilibrium concentration of HI? Well, we know what it's equal to. Equilibrium concentration of H2 is equal to X. This one's equal to 0.2 plus X. This one's equal to 3.2 minus 2X. Let's substitute what we know X to be. So the equilibrium concentration of H2 must be, and how many significant digits do they want? 2 decimal places. It must be 0.81 molar. The equilibrium concentration of I2 must be 0.2 plus 0.80945, which is 0.80945 plus 0.2, 1.01 molar. For HI, we take 3.2 and we subtract from that 2 times 0.80945. So 2 times 0.80945 and 3.2 minus that, 2 times 0.80945, 3.2 minus that answer, 1.58 molar. Now they asked us to calculate the equilibrium concentration of HI. So that is this one, and this is our final answer. We take this value and plug it into ALEKS. So at equilibrium, how much HI, what would the concentration of HI be? It would be 1.58 molar.